start.
It's working now?
Yeah, it's recording.
So here, let me pour some candy. So I'm going to go through the Weinberg's derivation of the Dirac spinors. It's not difficult, but it's technical and can be very confusing because there are three sets of plus or minus signs, and it's very easy to get them confused. In fact, there was a typo in the first version, the first printing of Weinberg's book. There was an overall sign that was let me also correct, there was a typo in equation 172. And of course, the upshot is simply that the rotation matrices for the 4x4 representation of the Lorentz group
Is this the defining 4x4 representation, or like the?
Yeah.
Okay.
And in fact, it's
There's more than one 4.
no, you're right. It's not the defining representation. It's
The stacks
it's what's called the one-half representation.
Okay, so that's
So here,
that's two block diagonal 2x2 representations.
yeah. So in other words, the J matrices for this representation are simply 1/2 sigma 0, 0, sigma.
What's between J and the other? What's that symbol on the top?
Well, this is just
Looks like a butterfly.
script J.
Okay.
And this is the same thing, really. I could have written it this way. But this is when you use two indices to represent the generators, then the rotation matrices are basically J sub j is epsilon ikj script jik with 1/2. Looks like that.
Is this, so there's sigma j and sigma prime j up here? So they're the same?
These are the same. There's no prime. That's just
Okay.
Yeah, last time whenever we did it though, we had like a minus sign for
yeah. There was
or is that no?
huh? There was I was off by a minus sign.
Oh, you were off by minus. Oh, okay. Yeah.
Well, I think I wrote
exactly
down the final thing correctly, but
Yeah. I was just wondering about this guy, JI0.
oh, those are the boost ones.
Okay.
The boost ones, I think I did correctly. Yeah, they are sigma I, right? The boost ones, which we could call KJ, are 1/2 sigma j 0, 0 minus sigma j.
Sorry.
Are you sick?
I was. I still am a little bit.
Let's see, can we open the windows at all? I guess
Will that just increase airflow and then
Yeah.
not. Not much airflow, no.
Yeah, no, it'll increase airflow and then it means the germs will get to you faster because there'll be more currents carrying you around the road.
Okay, so what we're going to do is we're going to write the Dirac fields this way. The positive frequency part is a sum over S integral dqp over 2 pi to the 3/2, and then some UL of P and S, and this is really vector P, but seems to me that we can put a full vector in there and it won't hurt anything. And psi L minus of x is a sum on S integral dqp 2 pi 3 halves VL of P and S minus I P dot X. And I call this B dagger of P and S. Weinberg uses A super C dagger, but it seems to be this is a simpler and more common notation. Okay, we had these rotation conditions, and these rotation conditions are sum on S, UL bar, these are at momentum 0, S bar, Ji of J, S bar S equals a sum on L of script J sub I. Now I'm going to these J sub I's. L bar L UL of 0 in S. Now what we know here is that L and L bar go from 1 to 4 because we're talking about the 1/2 representation of the Lorentz group. So they're 4 by 4 matrices. So these are 4-dimensional spinors. On the other hand, we don't know a priori what values S can take. And so what we're using here are the matrices that one learns about in quantum mechanics, but to start with, these guys are 2J plus 1 dimensional, 2J plus 1 by 2J plus 1 dimensional generators of the rotation group. And what we'll see is that they're actually 2 by 2. Or they're two 2 by 2.
So Kevin, I have a question.
Yeah.
It's kind of a general question, but
Yeah.
so these J's, are they kind of like stacked representations of different generators, but they're all of SO, all different representations of SO3?
These are, yeah, they're all generators for SO3, the
Different
rotation
representations,
group.
okay.
These are 2J plus 1 by 2J plus 1, and these are the 2 by 2s. In other words, they're these guys.
Okay. And here we're doing spin half, I'm guessing? Is the J a half here because of the spin half?
Well, that's the point. We're going to show that little j has to be a half.
Okay.
Right, left side.
So you get at least one. Good.
Left side doesn't have index S.
Give me that again.
The right side have an index S, but left side doesn't. When you sum over it.
Yeah, I guess he's saying.
Yeah, I guess you're right. That should be summed over S bar. Actually, I'm running out of candy very quickly, so I'm just going to give one candy for anybody who does anything gets one candy.
So we've already, so only Austin can make any example?
Let me put down the second rotation condition. It's again, yeah, it was an S bar in my notes. Sum over S bar, VL bar of 0, momentum, S bar. And now remember, because these, let's see, actually, just to remind both of us, all of us, the spinor conditions okay, well, some time ago, what we showed was that the matrix here was the complex conjugate of the rotation matrix. And so what we have here as the rotation condition is, and we've had this before, this is minus Ji of J, complex conjugate, and yeah, the J should be in there actually, S bar S. So So I've got, what I actually have is one parenthesis in there. Okay, that is then equal to a sum on L of the ith rotation generator, the L bar L matrix element, VL, zero momentum, S. So these are the two conditions. And remember, the J's are these guys. And so what we've actually got here is we have L taking four values, and these four values are U1 of S, U2 of S, U3 of S, U4 of S. You can think of them as a vector there, and we can rewrite these as U plus, because the pluses are the ones that go up here, and the minuses are the ones down there. And so this is U plus a half of S, U plus minus a half of S, U minus a half S, U minus a half S. So it looks like that. And a similar notation for the B's, B1 of S, B2, B3, B4, all of S. And what we've got is B plus 1/2 of S, B plus minus a half S, B minus a half S, B minus minus a half S. Okay, so that's the notation. And then, if we look at these equations, we can recognize, we can split them into four equations because each of these split into a plus equation and a minus equation. So we have a plus equation and a minus equation, plus equation and a minus equation. And so what this looks like then is sum on S bar, U plus M bar, and I'm gonna leave out the zero momentum. It is zero momentum, but I'm not going to say so explicitly, because I think this will be clearer here. Now we're summing over M and plus M. Well, we're just going to plus, so we're just summing over M. And this is 1/2 sigma I, M bar M. And then this is U plus M of S. So the plus part of this equation looks like that. The minus part looks entirely similar. So it looks like that. If I were you, I'd move over.
A little bit. Appreciate all that we have.
Here we've got a sum over S bar, V plus M bar of S bar, and here we have minus Ji of J star S bar S equals sum on M here. So I see I've got a couple of typos there. Sigma I, M bar M, V plus M of S. And then finally here, sum S bar, V minus M bar, S bar, minus Ji, J complex conjugate S bar S equals sum half sigma I M bar M E minus M of S. Okay, now we can notice that what we've got here is a matrix. These matrices, these V's can be looked at as matrices where M, being part of an index on a Pauli matrix, takes the values plus or minus a half, but where S bar takes one of 2j plus 1 values, it will turn out to be only 2, but for the moment it's 2s plus 1. And so we can rewrite this as a matrix U plus MS is going to be U plus sub M of S, or minus, and V plus or minus MS is going to be Vm of S plus or minus. So if we define those matrices, then what we have these equations are equivalent to, in matrix notation, U plus Ji of J equals a half sigma I U plus or minus. So maybe I'll just write them all down. U minus Ji of J equals half sigma I U minus, and then this one though is more complicated. It's V plus minus Ji complex conjugate of J is a half sigma I V plus, and then V minus minus Ji star of J is a half sigma I V minus. So we've got our now 4 matrix equations. But now Weinberg uses Schur's lemma. Schur's lemma is something you can be sure about. And it's derived in my notes on group theory, which I put the whole chapter 10 on the class webpage, and it's, I don't know, it's section 7 of chapter 10. Yeah?
Yeah, I was wondering, so I just missed it, like the matrix U, is U a matrix, or is U a...
Well, here,
Yeah.
you started out as just these spinors.
Yeah.
But now I've suppressed the 0 because everything's at 0 momentum.
Okay. Yeah.
And then I've decomposed the 4 L's into spin up, spin down, plus and minus,
Yeah.
corresponding to these two.
Sure.
And so then this thing is a matrix in the sense that this is M bar S bar. This is U minus of M bar S bar. This is U plus M bar S bar. So these are.
Okay.
I didn't write this very well. This is just U and that's V.
I see.
So these things look like this. But this is, all right, there are two observations. First is that, of course, the Pauli matrices provide an irreducible 2x2 representation of the rotation group. It's irreducible because, of course, it's the simplest representation of the rotation group. These matrices here, by definition, are they're the 2j plus 1 dimensional irreducible representation of the rotation group.
So we've got two irreducible representations of the rotation group. And so what we could do with these equations, you see, is we could dot the ji with a vector and then multiply by I, say, and then exponentiate it on both sides, and we could then have something like this: u plus e to the, say, I theta dot jj would be e to the I theta dot sigma over 2 u plus. So we have equations that would look like this. And also a similar equation for these. And so what Schur's lemma says is that if any matrix commutes with all the elements of an irreducible representation. Actually, I didn't bring the exact statement of Schur's lemma with me, but it's, let's see if what Weinberg said explicitly. All right, well, he just said what I was going to say more briefly. But whenever you have this, Schur's lemma tells us that u plus or minus must be a multiple of the identity. And,
But it's, the dimension is not.
hmm?
It's not, the dimension does not match this matrix.
C plus or minus times the identity.
You can't say.
But the matrix U is 2j plus 1 with 4 or 2, I guess.
Yeah.
How do you do?
I don't understand what you're saying. Say it again.
U is a matrix, right? U is a matrix.
Yeah, U is a matrix, and if it commutes, if it connects two different...
What is the dimension of the matrix?
That's the point, you see. What we have here are implicitly two irreducible representations of the rotation group. Now, the statement is that if this is true, and this is an irreducible representation of a group, then U has to be a multiple of the identity. So U started out as being 2 times 2j plus 1, but since it's a multiple of the identity, we now know that j has to be a half.
Yeah, I think there's another part of Schur's lemma that I think you left out whenever you said it, which is if you have that this matrix commutes, like if you commute this matrix through one representation and you get a new representation, the idea is that those two representations actually have to be the same.
Have to be equivalent.
Yeah, they have to be equivalent. They have to be equivalent.
Right.
So that way you know that J is...
Right. So the way Weinberg says it is that U and V must either vanish or be square and non-singular. That's right. I should have just read what he said, or maybe what even is in my notes here. Let's see, what did I say? Yeah, it's what I said was, okay, so this is equal to, in other words, some matrix S such that the determinant of S is not equal to 0. And the same thing here for V. And now it turns out then that since sigma is 2 by 2, J has to be 2 by 2, and so what we're saying here is that J is equivalent to sigma, and in effect we might as well just set J equal to just J equal to the, just S equal to the identity. And then for V, or U equal to the identity, for V, since this is 2 by 2, we know that the V relation is minus, it would effectively be minus sigma I star, and we know that that's sigma 2, sigma I, sigma 2. So we can set V equal to, V plus or minus is effectively equal to sigma, is proportional to sigma 2. And so what we do is we set U plus or minus sub ms is C plus or minus delta ms, and V plus or minus ms is minus I d plus or minus sigma 2 ms.
So why are we saying V plus minus equals sigma 2? Why are we saying V plus minus equals sigma 2?
Well, in general, they could be two different constants. In other words, as I said, this is a multiple of the identity, and this is a multiple of sigma 2 because of this.
Is that like another part of Schurzman? That if it, yeah, about like anti-commutation relations, or no, I guess you can exponentiate this guy too. I think it's something similar.
Wait, so the first part of Schurzman is like, so if a matrix commutes with,
I didn't bring the notes for.
but if a matrix commutes with every element of a single irreducible representation of proportional to the identity.
All right. I'll get you.
And then, so here we have two different ones and they commute. Is that a second part that tells us that?
Yeah.
Because here we don't know that U is proportional identity. If it was proportional identity, then we would know that they were the same, but we don't know that right now. So what property are we using?
No, yeah, you can also there's like an alternative sort of form of Schur's lemma that is for if you have different representations on both sides. And it says they have to be equivalent up to some similarity transformation.
So here we basically conjugated.
Yeah.
We conjugated the e to the I of aj, or one of them by this U. And then we got a different one, and so then they're equivalent up to.
Yeah, yeah. So at least j should equal a half.
Okay.
Is one thing. But I'm kind of confused about the down here because it's like, yeah, it's anti-commutation relations.
Yeah.
And so by that he's saying it should be sigma 2? I don't know, it's kind of strange. I've never seen something like that.
You have V, right?
All right, so
The Bible.
all right, so let me state it in detail then. So there's part 1. If D1 and D2 are inequivalent, irreducible reps of a group G, and if D1 of G, A, is equal to A, D2 of G, for some matrix A, and all G, then A must vanish. Okay, well we don't want, so what that, so let's go back to this case. This is what we had to start with. Then I said you could multiply this by, multiply this by I theta, dotted into J. So you'd have something like this, U plus theta dot J is a half theta dot sigma U plus. And of course this also works for just the identity, and it works for theta dot A, theta dot J squared, and so forth. You can iterate this, you eventually get an arbitrary element of the rotation group like that. And so that tells us either these two are equivalent, or U plus vanishes. Well, if U plus vanishes, there would be no fields at all. And so consequently, you get that these two representations are equivalent, and so they must be related by a non-singular matrix S. That is to say, U plus. All right, let me write down the second part of this, just for completeness. So part 2 is if for a finite dimensional, so a finite dimensional irreducible representation P of G, we have D of G, A equals A, D of G, then A is a constant times the identity. Okay, so that's the, so we certainly have a finite dimension, we have finite dimensional irreducible representations here, and therefore A is a multiple of the identity. So that's why, in fact, this U is not simply S, but it's just a multiple, C plus or minus of the identity. And then in the second case, we're dealing with, once we know from the first case that this is the 2x2 case, then this has to be I'm just well, I seem to have one extra S that's not just the identity, but if V minus is sigma 2, then it satisfies this with the J being the normal Pauli matrices. I guess there's a...
I mean, it's kind of weird too with the complex conjugation, because, well, I don't know, maybe that would clear things
well,
up.
we know
Like
it's two, well, from the U case, we know that J is a half.
Yeah, sure,
So
sure.
since J is a half, these things are either the Pauli matrices or some equivalent set of 3 matrices.
Yeah, I'm just trying to think of how I resolve that with the Pauli matrices. If you complex conjugate them, sigma 2 changes sign, but the other two don't. Does that help us?
Actually, you know what I just thought one could do for this? Suppose you complex conjugate everything.
Okay. Everything
So then,
both sides of
so
the
yeah.
equation?
So then what you get is you get the equation V minus complex conjugate. Now you're going back to J, I, is equal to, say, minus sigma I complex conjugate V, well, I did minus, sorry, plus or minus complex conjugate, okay? So now what we say is that minus sigma I star, this is equal to a half sigma 2, sigma I, sigma 2, V plus or minus complex conjugate. And now we multiply from the left by sigma 2, so we get sigma 2 V plus or minus complex conjugate Ji equals a half sigma I, sigma 2 V plus or minus complex conjugate. And so then these structures here have to be the identity. This has to be a multiple of the identity. And if that's a multiple of the identity, then V is a multiple of sigma 2, and just since we already have an arbitrary number here, Weinberg chooses a minus I to make it simple. Okay, so you forced it out of me somehow. So now we come to the hard part, keeping track of all these indices. And the only way I got to get this straight was actually to write down all 8 cases. Well, for the case of the U's, it's kind of obvious what's going on. U plus or minus MS is C plus or minus DMS. Okay, so what that tells us then is that that this thing that we had, U1S, U2S, U3S, U4S, that was U plus a half of S, U plus minus a half of S, U minus a half of S, U minus minus a half of S. And this then is C plus delta of a half S, C plus delta minus a half S, C minus delta a half S, C minus delta minus a half S. And of course, this would just be C plus 0, C minus 0. So the U spinors, the U spinors then are U of 0 for M equal to a half. What do we have? We have C plus 0, C minus 0, and the other one, U M equals a minus a half, is 0, C plus 0, C minus. So in other words, since this is just the identity, it's when it's M is, if M is a half, S has to be 1, has to be a half, not 0. If M is minus a half, it has to be minus a half and not 0. If it's an upper thing, it's C plus, a lower thing, C minus. Now for the case of V minus, what we have here is that this choice here of V plus or minus MS equal to minus I, D plus or minus sigma 2 MS. Well, this is a matrix. This is D plus or minus 0, minus 1, 1, 0. Okay, and what are the indices here? The row index is M. So row M, column S. So now if we keep that picture in mind, namely that D plus or minus is d plus or minus 0 minus 1, 1, 0, where it's row M, column S. We then have V plus, say, of 1/2, 1/2, well, that's clearly 0. V plus of minus 1/2, 1/2, well, this is going to be D plus because this is row minus the second row and the first position, first column. So that's D plus. Then we have V minus 1/2, again, of this thing here. This is S, and this is M. And so now this is, they have the same value, so it's 0. And then we have V minus 1/2. Oh, wait a second, I'm sorry. Yeah, this is okay, all right. Minus 1/2, 1/2. Okay, so this is, again, the lower row, first position, so that's a plus. And so that is D minus. Okay. Then, so what does that tell us? That tells us what that tells us what that tells us that V of 1/2, or if you want explicitly, V 0 1/2 is equal to, the top one is 0, D plus 0, D minus. So that tells us what the spin-up spinor is for the antiparticle. And then the other cases are B plus 1/2 minus 1/2. Well, this is going to be a D plus, and now M is 1/2, so it's top row, but second column, so that's a minus sign. V minus 1/2 plus minus 1/2, that's 0. V plus 1/2 minus 1/2, so this would be minus D minus. It's the same logic as here, but minus, and V minus 1/2 minus 1/2 minus 0. So that tells us that V of 0, M equal to minus 1/2, and maybe I would make this more clear if I said this was M equals plus 1/2. This is equal to then minus D plus 0, D minus 0. And let me just check that. Yeah, all right. So the very top one is minus D plus, and the second one down is minus D minus. So those are the basic spinors, and this is essentially the most confusing thing we'll do this year, I hope.
You said that about something else like 3 weeks ago.
Did I?
Yeah.
What was it?
Something else of using.
It was deriving these conditions for boosts and rotations.
Oh, well, it's the same ball of wax, isn't it?
Same ball.
All right, so now that we've got this basic, by the way, let me just mention in the first printing of Weinberg's book, Weinberg's volume 1, in equation 5.5.5, you had a minus sign error, so I'll just write this down. It should be minus sign, E plus minus, times sigma 2 m sigma. So he uses sigma, whereas I just use s. Okay, the spinors of finite momentum are what you expect just from what we've done many times before. It's just a canonical m over p0, a Lorentz matrix times u of 0 and s, and v of p and s is same thing, m over p0, d of l of p, v of 0, and s here, s is equal to plus or minus a half. Okay, so this constant c plus and minus, d plus and minus are somewhat arbitrary, but if you want the field to transform nicely under parity, then you need a certain relation for them on these. They're to transform properly under parity, then the d plus or minus and c plus or minus can't be totally arbitrary. So what do we want to happen under parity? So I'm going to use Weinberg's notation here. This is eta complex conjugate a of minus p and s. So parity flips the momentum, and on p dagger of p, it's eta p dagger minus p and s. Well, he uses an eta with an extra, he allows for an extra phase here, but I think eventually, all right, I'm going to suppress that extra phase. In any event, P psi L plus then of x, the inverse is going to be eta star sum on s integral dq p 2 pi to the 3/2. And then this u of L of what? Well, it'll be the a of p will be a of minus p, but then if you change p to minus p, you get back, you wind up with u of minus p, and then you can compensate in the exponential for the, in other words, you have I p0 minus p dot x, but you can equally well flip the minus sign to the space part, and so then what you have is e to the I p dot t minus x, a of p and s. And the same thing on sine minus L of x. And, all right, I'll put in Weinberg's C there. Sum on S, integral dqp, 2 pi 3/2 VL minus P and S, e to the minus I P dot T minus X, E dagger of P and X.
Wait, I missed it. So why doesn't the P and the A, if that's the, what's the parity?
Okay.
Yeah, I'm sorry I missed that.
What you have here then is an integral dqp, UL of P and S, A of minus P and S, E to the I P dot X.
Yeah.
Okay, leaving out extra factors.
Okay.
Now we let P go to minus P.
Okay.
PQP, UL minus P, S, AP, S. But now, what do we have? We have e to the I, P0 minus P dot X.
I see, yeah, I see.
So then you can flip the minus of the spatial part of the momentum to the minus of the spatial part of the position. And when you do that, you get this. And Weinberg writes P minus X as script P on 4 vector X.
Okay. Do we pick an overall minus sign, or do we just not care about that? When we go from like P to minus P.
Well, there's a minus sign. This is the negative frequency part. Well, I don't understand which.
I guess when you're going from like P to minus P, you kind of, when you replace the integrand, when you place the D3P,
D3P just goes into D3P.
Okay, never mind.
I admit that things like that can be confusing. Okay, so now last time we learned some nice things about how, remember, beta is essentially the parity matrix. Beta is the parity matrix, and we learned that U of minus P and S was square root of M over P0 beta D of L of P beta U of 0 in S, and the same thing for V. Now, what is this saying? What this is saying is that when you have a beta on a Lorentz operator, it doesn't affect rotation, but it affects boosts, and it inverts boosts. And consequently, it takes P to minus P. See, without the betas, this would be U of P and S. With the betas, it's U of minus P and S. And this is something I just sort of stated last time.
These betas are like a representation of the parity operator?
It's the parity matrix, effectively.
Okay.
Well, it's parity in certainly in that sense. So let's see, whose copy is this now?
That's fine.
That's yours? And I'm just wondering, is this the one that has corrections?
I don't know.
Huh? Shit. No, it doesn't. Where did you get it?
Amazon.
Oh, you got it from Amazon.
Yeah.
I think you have a right to complain.
Why?
Because it's not it's an early printing before they printed it with corrections.
Really? Wow.
For example, if we go to this page here, I think we'll find this. Yeah, see, the minus sign is missing. So I mean, you know, it's dishonest for Amazon to sell an early printing of a book in which a later printing has corrections.
Yeah.
Because you have a copy that has a later printing with corrections, right?
I don't know which print it is. I can take that. I don't have that now. I don't have the book now.
Yeah, but I looked at it on Tuesday or last Thursday, and I saw that it had corrections.
Kevin, will you help me draft a complaint email to Amazon?
What?
Will you help me draft a complaint email to Amazon?
I'm sorry, say it
Will you help me draft a complaint email to Amazon?
again. Call them up. Don't bother with email.
Call
them? Yes, you call them up.
Oh, what should I say? Can you coach me? I don't know what to say. I've never done that before.
I bought a copy of the book, and instead of sending me the latest printing of the book, you sent me an early printing that by now is, let's see, 95? 95, 05, 15. It's 23 years old.
Oh yeah. What if they say
And maybe 20 years ago or 22 years ago, and Cambridge published a corrected version. And in fact, I sent Weinberg maybe 100 typos, and he fixed them, and other people sent him typo corrections. So Cambridge is a responsible publisher, unlike Elsevier and Wiley. And so you call them up and bitch and say you want to send this back, and you want them to send you the latest printing of the first edition.
There's like hundreds of typos in here,
Yes.
so it's not a very good book when it first came out.
Well, I mean, in a book of that size, it's amazing that there were only 100. So it's not that Weinberg was careless, it's that just, if you write a novel, there aren't going to be many typos. If you write something with detailed equations, you're going to get a gazillion typos. Just the way it is. All right, so let's see what we have. So far we've noticed here then that we've seen what U of P, actually maybe I should go out to the last board here. Suppose, so we're over here and we're saying that under parity the thing transforms this way. UL of minus P is this. And what will this be? Well, this will be beta U of P if beta U of 0 is simply related to U of 0. So in other words, what we just saw, all right, this is apparently dead. I don't know what happens to these pens, that somehow they... So what we've seen here is that U of minus P and S is effectively beta times, it will be beta U of P and S if beta U of 0 and S is just a constant times U of 0 and S. And that constant he chooses to call B sub U, U of 0 and S. And similarly, the field will transform nicely under parity if beta, remember, is the 4x4 matrix 0, 1, 1, 0. And it's I gamma 0.
Yep.
If I'm...
Why was that parity again?
Okay, the reason is that beta is I gamma 0,
Yeah.
So beta anti-commutes with the spatial gammas, but not with the temporal gamma, not with gamma zero. That's
okay.
why it's, that's
But
why
it's not like, it doesn't represent a parity inversion on the general 4 vector. You act that on
No, this is, I tell you, we're all gonna be bloody dead by the end of the week. With all this coughing and the number of virus particles in this room,
Oh, yeah.
colossal.
Yeah, kill everybody, Kevin.
What was your question?
Oh, I was asking, yeah, like, so this doesn't represent parity inversion on like a general 4 vector. Like,
No,
I'm
it's
asking-
parity on a Dirac matrix
On the Dirac.
and consequently on Dirac fields and so forth.
Okay. Mhm.
So the idea is that beta gamma is 0. Okay, and we call this then beta V of V. All right, and we want these to be just signs because parity squared is 1, so b sub u squared equals b sub v squared equals 1. So now the fields transform nicely under parity. P psi plus L of x, P inverse is eta star b sub u beta psi plus of px. That's parity on the 4 vector, just flips the spatial part.
Sure.
And let me just put a minus sign here.
Let's see.
U or V. Okay. So now you can adjust the overall scales of the fields, and what you wind up with then is this, that U of 0 1/2 is 1 over root 2, 1, 0, BU 0. U 0 minus 1/2 is 1 over root 2, 0, 1, 0, BU. And V of 0 1/2 is 1 over root 2, 0, 1, 0, BV. And UV of 0 minus 1/2 is minus 1 over root 2, 1, 0, BV 0. And, right, okay. So that's what we've got at this stage. The next thing is to say, well, can we make something that's causal by taking kappa psi plus of x plus lambda psi minus of x, and we will want that it's space-like separations, either the commutator or the anti-commutator of psi of x, psi dagger of y, and psi of y. What is this? This was supposed to be plus or minus. So we want, at space-like separations, that the field should either commute or anti-commute, both with itself and with its adjoint. And the freedom we have then is to choose kappa and lambda, and to choose the phases BU and BV, or the signs. BU and BV are just plus or minus 1. And, well, I think I will just say that what's involved then is what's involved is a somewhat detailed calculation. Let me tell you what the bottom line is. In other words, what's the actual answer? The answer is that what you need is that kappa squared is minus or plus lambda squared. You also need that kappa squared is kappa squared times BU is equal to plus or minus lambda squared BV. So in other words, you take these expressions, we have expressions for the field in terms of the spinors, and now the spinors have an extra BU or BV. There's some cranking that Weinberg skips, and in order to get these, we need these two conditions. And so what's possible? Well, if we choose the bottom sign plus, then this is equal to that, and if those two are equal, then we take BU can be minus BV. If we chose the upper sign, well, obviously we have to choose the bottom sign because we can't have a minus sign here. I mean, that would just be stupid. Well, that's values. So we have to choose the bottom sign, and then we simply get that magnitude of kappa equals magnitude of lambda, and BU is equal to minus BV. So these are the conditions that we get. The minus sign means, actually, I wrote this down actually incorrectly because he uses the convention minus plus. So we have to take the bottom sign is the anti-commutator. So what this tells us then is that the spin 1 half fields are fermions. And so what we've got then is that fields that represent spin 1 half particles are fermions. They obey anti-commutation relations, and we fix that BU and BV differ by a minus sign. And at this point, one might as well just set BU equal to minus BV equal to plus 1. There's always an arbitrary phase that one can choose, but there are only so many arbitrary phases, not an arbitrary number of arbitrary phases. And so at this point, one has a complete definition of this field, psi L of x. This has 4 values here, and it is a sum over S and an integral dqp over 2 pi to the 3 halves. And then the rest here is U sub L of P and S, e to the I px, A of P and S, plus V sub L of P and S, e to the minus I, P dot x. Okay, A conjugate, or more simply B dagger of P and S. And these remember everything, the spinors at finite momentum are Lorentz transforms of the spinors at zero momentum. And so the key thing is to say what the spinors are at zero momentum. And these are 1 over root 2, 1, 0, 1, 0, which is what everyone would expect. U of 0 minus a half is 1 over root 2, 0, 1, 0, 1. But what's somewhat surprising is that V of 0 a half is 1 over root 2, 0, 1, 0 minus 1, and V of 0 minus a half is 1 over root 2, minus 1, 0, 1, 0. So these rotation conditions, together with this minus and the complex conjugation, have implied that the V's are somewhat different. So recall that this statement here is that BV is minus 1. This 1 here is, these 1s are BU equal to 1. These minus 1s are BV equal to minus 1. And let me just, yeah, there was an overall minus sign here, but that canceled the fact that BV was minus 1. And so these are the final momentum 0 spinors. And so then under parity, P psi of x, P inverse is an arbitrary phase, typically times beta times psi of P and x. And the field obviously satisfies the Klein-Gordon equation because it's EPI px, e to the minus I px. But it satisfies another equation, the Dirac equation. Yeah?
Oh, I was going to ask about the normalization with the, so I remember before whenever we were talking about the spin 1 scalar fields and spin 0, or the spin 1 vector fields and the spin 0 scalar fields, it's a factor of the square root of twice the time-like component of momentum.
Say this again. What are you saying?
Yeah. Okay. Sorry. So before, just in other field theories that we had constructed, there were, in the normalization there was a square root of 2p0.
Oh yeah.
Yeah. So why is that not here?
Well, it is here, but it's hidden.
Okay.
Or something like it is there, and the way to see that is to go back here. Here, turn the camera around maybe. There's the square root of p0 in the denominator.
So okay, so it shows up.
So,
It's embedded, it's inside of the spell.
I mean, if there hadn't been, in other words, if we hadn't had the minus sign there, it would be u of p and s would be square root of m over p0 d of L of p, the standard Lorentz transformation, the 4x4 1/2 representation of the Lorentz group on u of 0 and s. So it's that's the thing there. Good question.
Sweet.
So the
Can I have a question going back a little bit? So,
yeah.
Actually, never mind. Let me think about it.
So what's the question? I'm afraid to get too close to you. So why don't I stand back here and speak in a loud voice?
So I don't know. Just what's the dimension of the u's and the v's? I'm confused.
What's the dimension of the
Because you
spinors?
have a matrix acting on them, so they're vector, right?
The u's and the v's
So
are.
like -1/2 to 1/2. So there's two.
The s is plus or minus a half,
Okay. So okay.
and the L takes 4 values.
Okay. And the beta. Okay. I see.
Beta is a 4x4 matrix.
Okay.
And when I wrote it at
Beta's
0, 1,
okay, that's what I was
0.
asking. Yeah, I was really confused about that.
Yeah. If beta, when I said betas,
Is it like zero identity?
yeah, it's really
blocked.
0, 1, 1, 1, 1,
Okay.
looks like that.
Okay.
Weinberg derives the spinor, the Dirac equation in a rather super complicated way. I mean, it's correct, of course, but it's anyway. The Dirac equation then is and this thing is often written as d slash. All right, I think we're basically out of time, so I think we ought to just quit at this point. Any last question?
Yeah, I have one final question. Yeah,
All right,
so
what's the final question?
yeah, this is something that I was reading about in another book. Like, you can write down a Lagrangian density for these field theories, and by doing variational calculus, you can come up with something like
Yeah, that's the normal
equation.
way to do it.
Yeah, so what is like
Wow,
the
double.
Lagrangian that you would use here to come up with the
Dirac equation.
Dirac equation?
Why?
Or no,
Why
what,
use it, or-
yeah, no, just what's the Lagrangian density that, I don't know, do you?
Oh, you want to know
just
what
write
it is?
down?
Yeah, actually, this is sort of tricky, actually.
Okay.
It's, the Lagrangian is the Lagrange density is something like psi dag of beta, and then it's gamma A dA plus M psi. It looks like that. Apart from an overall factor, and this could be plus or minus, and there might be an I. Okay, it's the Lagrangian. Weinberg writes it down in chapter 7, I think. Yeah, it's equation 7534,
Okay.
and actually I got it right apart from an overall minus sign. All right, let's quit now.
Yeah. Oh, but another thing too, you said this thing also